Greetings, everyone, and welcome to your first lesson in our course of study on Regents chemistry. As we do in a lot of your science classes, we tend to start with the scientific method, usually a review, and sometimes a little bit of an intro into scientific measurement. Depending on the type of science, scientific measurement can look quite a bit different. So we'll take a look and see what scientific measurement means in chemistry, along with the scientific method today. Now, as I said, scientific method is and should be a review. And what exactly is it? Well, it's kind of a way to solve problems. And we're going to start right in the middle here where it says start. And we tend to start with the problem. When we have a problem, the first thing we want to do is kind of do a little bit of research and see if anybody else has run into the same problem. We can kind of see if any other data was collected on this problem, if any conclusions were drawn about this problem, and it'll kind of help guide us to what we want to try and figure out and solve about the problem. And maybe we even adjust our problem or our question based off of the research and prior knowledge that we found. We then develop a hypothesis, which really is an answer to our problem that we're then going to develop an experiment to test. So after we come up with a logical answer to our problem, we then develop an experiment that we can use to collect data that's either going to support or not support this hypothesis. And we always test only one independent variable. The dependent variable, which we'll cover in a later lesson here, is going to be what is measured. From the experiment, we then can collect some data. And the data, this is going to be observations or some type of measurement that's collected from our experiment. But this is and should be concrete numbers that we can then analyze to see if it's going to support our initial thoughts on our problem, our hypothesis. We can graph the data, analyze the graphs, look at the relationship between x and y axes. Depending on what we can find, we draw a conclusion on, hey, does this solve our problem, yes or no? Was the hypothesis supported or not supported? And we always want to use the data to support that. Having data makes your argument stronger than if you were to not rely on any data at all. You could say that the Buffalo Bills are the best football team in the world, and sure, that's your opinion, but once you start to back it up with data, and maybe they do have the best statistics out of any football team, and if you can support that with data, then it makes your claim stronger and could then change your opinion into fact if it's supported by data. So I'm going to run through two quick examples of how we can use the scientific method, not just in science, but in general. Pretty much every day in any type of situation that you have, you can use the scientific method. So the first example is Jimmy coming to his mother complaining of the sniffles. And you can fill this out in your notes. The problem is that Jimmy has sniffles. Now, the hypothesis is going to be an answer to our problem. Well, why does Jimmy have the sniffles? Well, I think that Jimmy's sick. And because he's sick, that's why he has the sniffles. I don't know that he's sick. The hypothesis of Jimmy being sick can be tested, and that's what we got to try and do next. So we're going to develop an experiment, and this doesn't have to be complicated. Oftentimes we think of it as being complicated, but we're going to come up with an experiment to test whether or not Jimmy is sick. And to do that, I'm going to record his temperature 3 times per day. Data comes back. He's got temperatures of 102, 103, and 101. We can graph that. We can find standard deviation. We can find means, averages. We analyze that data. Maybe we come up with the mean being 102 Fahrenheit. Okay, well, we thought Jimmy was sick because he had the sniffles. We recorded his temperature as means of our experiment. We collected some data. We analyzed that data. We found the mean of that data. A fever or a temperature of 102 Fahrenheit means he has a fever. So Jimmy has a fever and is sick. And this is supported by the data that we collected from our experiment of recording his temperature 3 times per day. Now in the next scenario, Emma goes to start her car and it's not turning on. Well, the problem is Emma's car doesn't start. So the hypothesis, we want to try and come up with an explanation to our problem. Sometimes this is right, sometimes it's not. So let's say maybe Emma's thinking, well, my battery's dead. Is it? I don't know. Maybe. Could the starter be broken? Could your key be broken? Could it have been struck by lightning and everything electric in the car doesn't work anymore? Sure. But this is just one logical explanation. And our experiment will help us determine if it's supported or not. And if it's not, then we have to come back, revise our hypothesis, and try again. So the experiment, to see if the battery's dead, let's test it with a voltmeter. And we'll see what the voltage is on the battery, and then we can see if the battery is dead or not. We get a few readings that come back. 11.0 volts, 10.9 volts, and 10.6 volts. We analyze this data. We come up with a mean of 10.8 volts. In our analysis, we determined that a good battery is 12.6 volts. And we have 10.8 as our average from the data that we collected. So our conclusion, since we have a voltage that is lower than a good battery of 12.6 volts, our conclusion is that the battery is dead. And let's try replacing the battery and trying again. So this is an everyday scenario that you might come across. And you might not always think that you use it, but you use it in a lot of scenarios. And the part that in an everyday case of using this to solve problems, the part that might not be as formal as it usually is the experiment. But in general, if we have a problem, you're thinking about how to solve it, and you're finding some type of data, something that can support your thoughts here of why you're having an issue with something. My phone's not turning on. Well, why isn't it turning on? Is it a button? Did I charge my battery? Did I drop it last night? Your experiment might be checking the case, might be looking for cracks. It might be trying to change a battery out, changing your charger. We can then collect our data, analyze it, and see if any of that supported our initial thought of why the phone wasn't working. So we're going to shift gears here into the metric system, which I have a little story that I'll share with you momentarily here about how great the metric system is and how poor the standard system is. So this was devised in 1960 by the General Conference of Weights and Measures. It has some fancy French name here that I don't like to pronounce because I can't speak French. But the conversions in this system are all in base 10, meaning that the decimal only moves by one place between each different prefix. We count up to 10, we have a different prefix. We count up to 100, we have a different prefix. And all of our numbers are based in that standard of 10. These prefixes are used to determine our magnitude of a particular unit. So we know that kilo always means 1,000. Or centi means 1/100th. Or the kind of the opposite of kilo, 1/1000th would be milli. Now there's a couple tables we'll look at here from your reference tables. First one's table D. This is on the front page, and if you don't have those, make sure you take those out and take a look at those and start getting familiar with them. There are selected units here for different measurements. We have meters, grams, Pascal, Kelvin, mole. Each of these we're going to use at some point throughout this year. So this is a good spot to reference. It tells you what the quantity is measuring, length, mass, pressure, temperature. This is a good spot to review all of your different units that you might come across. And if you're unsure of one, this is a good spot to review that. Table C has our selected prefixes. These are selected prefixes. This is not all of our prefixes, but these are the ones that we will mostly use. And we tend to use micro, milli, and kilo pretty often in this class. The factor here tells us how big that number is. So 10 to the third, and all these things are base 10, all start with a 1. And the factor tells us how many spots that decimal is moving. In this case, it's moving 3 spots to the right. So we add 3 zeros to the end. So kilo means 1,000. Deci, with a factor of -1, means the decimal moves 1 spot to the left. So this becomes 0.1. Okay, we're all starting with a 1. The decimal spot's always to the right, and that exponent tells us where we're moving it to. Now, anywhere around here, and you can put this on your table, if we're moving from a greater factor to a lower factor, or moving from a prefix higher on the table to lower on the table, we move the decimal to the right. So if we convert 1,000 kilos, let's say kilometers, into a decimeter, a dm, we compare our factors here, kind of like we would on a number line, and that tells us how many spots we have to move that decimal. And since we're going down the table, we're going to move that decimal to the right. So 1,000 kilometers, we move that decimal 4 spots to the right. 1, 2, 3, 4. And this becomes 10 million decimeters inside of 1,000 kilometers. And we'll do more with that later. If you are going up the table here, from a lower factor to a higher factor, we move the decimal the opposite way, to the left. That's a quick little shorthand of how to convert through your different metric measurements. Now, the metric system takes a little bit of time to get used to, so I have a couple different comparisons up here of stuff that we have in the standard system, which we use. And I'm going to share my story with you on this now of why this is so ridiculous. The other day, I was talking with Mr. Jankowski, and we were trying to figure out how many feet are in 1 meter. Now, it's easy to figure out how many centimeters are in 1 meter. It's 100, and everything's base 10 in the metric system. But how many feet are in 1 meter? We didn't really know for sure, so we had to look it up. And we got a number of 39.287 feet. Okay, so inches. That was not feet, that was inches. We then had to convert that into feet, which we said, okay, well, there's 12 inches in a foot, so we definitely have 3 feet. But now we have, it's not 3 feet, 0.3 inches. Well, I guess it is. But what's the actual measurement of 0.3 inches? That's a decimal that we don't use. We'd have to convert this into a fraction in order to figure out that it's 3 feet, 3 1/3 inches. So there are 3 feet, 3 1/3 inches in a meter. And that's just a difficult conversion to have to do. And we are one of 3 countries in the world that actually use a standard system. Hopefully someday we get to the metric system, but at least in science, that's all we use. So to kind of have a comparison here, distance between two cities, and the metric system we use kilometer, we're used to seeing miles. Okay, a typical 10-mile trek is going to be about a 16-kilometer trek. So a little comparison there. Volume of a container of milk, metric system we use liters instead of gallons. Weight we use kilograms instead of pounds. I think this is awfully difficult to try and say, oh, well, I weigh about 84 kilograms instead of 150 pounds. Length of a pen, centimeter is appropriate to use instead of inches, so they're kind of on a similar scale. Mass of a candy bar would use grams instead of ounces, and oftentimes if you look at a candy bar package, it'll give you different weights of measure on there. Sometimes some in the metric, sometimes some in the standard. Time it takes for a class period, kiloseconds we would use instead of hours. Or how tall we are, we would use meters instead of feet or yards. We're looking at something like 1.6 meters compared to 5.5 feet. A couple math rules for chemistry. N3, no naked numbers. All measurements have to have units written after the numbers. So any answer to a math problem, any measurement that you take has to have a unit written after the number. Otherwise, it means nothing. If you don't show your work, you don't get your credit. You got to show all of the following when doing math problems in chemistry. The equation we're going to use. This part here I kind of leave up to you. The equation rearranged algebraically to solve for the variable you're looking for. And I'll show you later, but I tend to do that while we're doing the work. Then plugging in your numbers into your equation, substituting units for all of your variables. So this is basically your numerical setup. And the final answer that I'd like you to box in and round appropriately to significant figures, which we're going to get through shortly. Now, why would a ruler have different scales on them, or in general, different measuring devices? Why would they have different scales on them? Each of these lengths from these 4 different rulers are the same length. But they all have different scales on them, and one of them is standard, the inch ruler on the bottom here, and the top one is metric, the centimeter ruler. Well, they have different scales because some can be more precise than others. For example, let's say we had a measuring chart on our wall in the classroom. And at the top, we knew it was 10 feet. Okay? And let's say we have, let's say Jordan comes in here. It's kind of a small Jordan. I'll make him a little bit taller. Let's say Jordan comes in here. You'll learn that I am awesome at drawing. He comes in here and stands in as a class. We say, okay, how tall is Jordan? We look at him against our little measuring chart here. We know at the top is 10 feet. And he is, I don't know, somewhere in the middle. Well, this would be a lot easier if we had some numbers down there, but we don't. So the scale here tells us that we can only read this accurately to the tens place. We can really only know if he's 10 feet or not. Anything in between there, we're going to kind of estimate, and there's going to be an introduction of error into our measurement. And this is very important in chemistry, trying to minimize error in measurements in really anything that we do. So if we're going to try and guess how tall he was here, we'd say, I don't know, maybe he's about 5 feet. Okay? Now if we put dashes in here, and we said, well, this is 5, well, now we have a finer scale. So we could say, well, maybe he's 5 feet and 1 inch. He's a little bit above the 5-foot line. Now our measurement's a little bit more precise. Maybe that's a little bit closer to what his actual height is. And it's the same idea here. If we are trying to measure something using this ruler, maybe I'll extend that a little bit or shorten it down. Okay, so let's say we go to the end of this line here. This measurement in between, we can get different numbers depending on which scale we use. And because we have finer tick marks in one ruler, we can make a finer measurement. So measurements are generally made one place beyond where the measuring device is marked. So when we measured Jordan's height here, well, our measuring device allowed us to read to the tens place. So we went one spot beyond that and estimated, well, he's about in the middle between 0 and 10, so maybe he's right about 5. So we're going to go to the ones place. We measure to the ones place. So in this first example, we have a line that comes to just beyond the 6 point. Our device has lines for every ones place. So we can estimate how close that line is between 6 and 7. There's no line to tell us what it is, but we can estimate that. And so we introduce human error into our measurement. Now, the finer that scale is, the more precise we can be, but there's still going to be error in reading the device. So we record this measurement as something like 6.3 or 6.2 centimeters, but that last decimal place, the tenths place, is going to be estimated. And the next example here, our scale goes by tenths, 0.3, 0.4, 0.5. So we measure one spot beyond the tenths place, which would be the hundredths place. So we're measuring how close we are in between 0.40 and 0.50. Okay, and I'd say that we're a little bit beyond maybe 3/4 there between 0.4 and 0.5. So that would give us something around 0.47 and 0.48. And this last place is going to be estimated because it's in between the lines of our measuring device. Accuracy and precision. When you guys do archery in gym, you probably talk about accuracy and precision. And this is a good slide to demonstrate both. Now, accuracy has to do with how close you are to an intended target. Could be with measurements, could be shooting arrows at a target. Now, these are accurate because they're all centered around the bullseye. They're not necessarily close to each other. There's a lot of scatter here, but they're all centered around that bullseye. Precision has to do with how closely your measurements are together. I think in archery we call that a shot group. These are not accurate because they're not near the intended target of the bullseye, but man, this is a consistent grouping. Okay, you might be off hitting the target, but you are doing the same thing every single time. Okay. D shows shots that are not close to each other and they are not around the bullseye. So that's neither accurate nor precise. So accuracy has to do with how close you are to a target. Precision has to do with how close measurements are to each other. Now, rules for determining precision. If our measurement has a decimal point in it, the precision is going to be the place that's farthest to the right in the measurement. So in this case, our precision goes to the last place here because we have that decimal point. And the last place here would be tenths, hundredths. This would be thousandths. So our precision is in the thousandths place. Next one, we have a decimal. Precision is going to be in the tenths, hundredths, thousandths, 10,000ths place. And again, we have a decimal, so precision is going to be farthest to the right. This would be the ones place. The next rule for determining precision, this one's important. If we don't have a decimal point in it, the precision is going to be the place where we either have the rightmost integer. In this case, this would be the ones, tens, hundreds. And if you are unsure of your place values, I did include that in your notes. So make sure you review that. Or where we have a 0 with a line over it. So in this case, this line is over the 0, right beneath it. And that tells us where the precision is. So in this case, it would be in the tens place. I'm going to give you guys two rules for significant figures, and this tends to be a little bit of a challenge for new chemistry students. This is how this rule is traditionally taught by a lot of teachers as the Atlantic Pacific rule. If the decimal in a number is absent, let's say we had 100, zeros on the Atlantic side, so on the right side, of the rightmost non-zero digit, in this case it would be the 1, are not significant. So these two zeros would be considered not significant. So in this case, 100 has one significant figure, or one sig fig. If a decimal is present, so let's say we had 100.0. Zeros on the Pacific side, or the left side, of the leftmost non-zero digit, which is going to be that 1, are not significant. So anything to the left of this 1 is not significant. Everything else, all other digits, are significant. So in this case, we have a 1, and the decimal makes these 3 zeros significant, so we get 4 sig figs. Now, the other way that we can look at this, and I tend to like this rule a little bit better. I think it's a little bit easier to understand. Zeros that appear before a non-zero digit are not significant. So these zeros in front of the 0.002 are not significant, so this would be one significant figure. This zero is not significant, so this would be 2. It's only zeros that we're going to not count as significant. Any non-zero digit is always significant, regardless of where it is in the number. If the zeros fall in between two non-zero digits, they count. The one in front here is not significant, and that's the rule that we have up here. Zeros that appear after a non-zero digit are significant only if they're followed by a decimal point. So this is the example we just looked at. 40 mils is one significant figure, that 4, but as soon as we have the decimal, this becomes 2. It makes the zeros at the end significant. If the zeros appear to the right or after the decimal, they are significant. So at the end of a number with a decimal, these zeros become significant. So in this case, 37.0 centimeters has 3 sig figs, and 4.100 has 4 significant figures. We'll do lots of practice with this so you can kind of get accustomed to these rules. And my advice to you, when you do work on these problems, keep these notes in general from 1.1 as well as these significant figure rules right next to you when you do your practice. Now, a group of civil engineers were at a conference being held in Central Australia, and as part of this conference entertainment, they were taken on a tour of the famous rock Uluru. This rock, announced the guide, is 50 million and 4 years old. Now, all these engineers who are always impressed by precision and measurement were absolutely astounded. How do you possibly know the age of the rock so precisely? Asked one of the group. The guy says, easy. When I first came here, they told me it was 50 million years old, and I've been working here for 4 years now. If you guys have any questions, make sure you write them down and ask them when you get the chance. Have a great day.